In 2022, a €30 billion effort to build the most advanced microchip factory in European history ground to a halt. The culprit was dirt. Here in Magdeburg, Germany, initial civil engineering surveys for Intel's mega facility hit an anomaly. Instead of the expected 40 centimeters of topsoil, excavators struck a 90-centimeter deep layer of humus-rich black earth. Local agricultural and environmental regulations mandate the preservation of this specific soil. Moving it required the careful extraction and relocation of over 3,000 dump truckloads of earth. That mundane logistical hurdle forced a full 12-month delay on the continent's flagship digital expansion project. Sustaining a digital society requires terraforming on a scale that physical geography and local law cannot always accommodate. Looking 200 kilometers southeast to the European semiconductor manufacturing company plant in Dresden, the scale of that terraforming shifts to fluid dynamics. Washing microscopic silicon wafers requires the heavy flow of the Elbe River. To keep the Dresden semiconductor cluster operational, the facility requires up to 67,000 cubic meters of ultra-pure water every single day. Extracting that volume without collapsing the local water table forced municipal utilities into a €300 million infrastructural scramble. By 2030, a massive river waterworks pipeline will pull water directly from the Elbe, solely to cool and wash silicon. Add to that a €400 million financial intervention to upgrade local 110 kilovolt electrical substations, a necessary step to prevent rolling blackouts across the regional grid. Europe's digital expansion is entirely bound by its geographic resource limits and the physical load capacity of an aging power infrastructure. Despite these massive physical investments, Europe continues to successfully subsidize older 28-nanometer chip factories, while entirely failing to produce leading-edge 2-nanometer nodes. This image of historical automotive manufacturing highlights Europe's true industrial engine. The continent's economy relies heavily on vehicles, which are bound to rigid, legacy code and aging hardware architectures. Modern vehicles operate on the AUTOSAR software standard, a system deeply tethered to older 32-bit microcontrollers, like the Infineon RX series shown here. These mature chips feature specialized physical layouts, including lockstep cores designed for error correction and guaranteed physical safety on the road. A €30 billion megafab producing state-of-the-art silicon ignores local demand. The European market requires the continuous, reliable operation of older nodes. The invisible constraint preventing the leap to newer hardware is the ISO 26262 A-Cell D functional safety standard. Translating legacy C code into automotive commands requires a specific, two-certified software compiler, like the Tasking VX toolset, acting as a strict bottleneck. Porting this safety-critical code to a modern multi-core array shatters its certification, risking catastrophic failure in vehicle braking and steering. Recertifying the compiler's software and hardware for a 2-nanometer architecture carries an astronomical financial cost, actively disincentivizing automotive manufacturers from upgrading. The massive state subsidies meant to launch Europe into a new generation of computing are currently offset by the legal and mechanical constraints of a software architecture that refuses to leave the past. Inside the pristine, isolated environment of a modern cleanroom, chip manufacturing relies entirely on ultrapure water. This liquid is chemically strecked and purified to a precise electrical resistivity of 18.2 megaohm centimeters. At this extreme level of purity, water actively seeks thermodynamic equilibrium, transforming into a highly aggressive, hungry solvent. If pumped through standard stainless steel pipes, this solvent state directly strips out microscopic iron ions, shedding lethal nanoparticles that destroy delicate silicon circuitry. Standard industrial infrastructure physically cannot survive inside a fabrication plant. The chemistry inherently demands specialized extreme resistance plumbing. The only physical materials capable of handling ultrapure water and the harsh hydrofluoric acid used in etching are fully fluorinated carbon chains. These unbreakable molecules are commonly known as PTFE, Teflon, or the broader industrial category of PFAS. This regulatory dossier represents the European Chemicals Agency's REACH Annex 15 restriction proposal. Drafted by 5 member states, The legislation seeks to completely ban over 10,000 of these PFAS chemicals to protect the environment. European policymakers are spending 43 billion euros to build semiconductor factories, while simultaneously drafting laws to outlaw the specific chemical plumbing required to run them. The drive for European semiconductor sovereignty has encountered a thermodynamic absolute, where environmental regulation has legally mandated the removal of the only materials capable of operating a modern fabrication plant.